morning, everybody. I'm very happy to be here. I have to say I'm particularly happy that I was not fist bumped, because then I wouldn't have been able to go back to one of my palaces. I wouldn't look good. Okay, so I did not know how much you are well-versed or how well-versed you are with respect to machine learning. So the talk is a little bit very high level, okay? If you have any specific questions, please feel free to ask during the question period or even during the talk, I don't mind. And certainly feel free to drop me an email afterwards so we can take this offline if needed. Okay, so machine learning. So the thing that I want to do is, if nothing else, I want you to leave from here with an understanding of what it is that we understand about what machine learning is, okay? And you see this is not particularly easy. Okay, so what is the problem? We all have heard about this, modern AI, this frontier AI as it's called, or they do amazing things, okay? They can predict really things that we were not thinking that were possible to be predicted before, okay? So the problem is that these models, these frontier models, are trained with data, of course, and this data may be problematic, or some of the data may be problematic. What does problematic mean? Well, it can, for example, back, there you go. So it could mean, there. So some data that's sensitive, okay, your personal data, okay? It could mean that some data is actually obsolete. It's no longer true. Facts in the ground have changed, that what the facts were when the model was trained. It could be that some of the data is biased. We've all have heard stories about using these modern AI models, and basically their inference is biased, okay, and the problems that this may cause. We also have heard problems with cyber attacks against machine learning models. I mean, this is a big issue these days. You hear of these national actors trying to actually damage the data with which particular models are trained, so that in the end the models are not going to be as good. Okay. And you can actually have humans making errors when they're producing this data. So we have this data that somehow it could be curated, it could be annotated somehow, and these annotations are crucial for the model in order to do its job correctly. And some of these annotations may be wrong. Think, for example, of classification labels for images when you're doing, say, image classification tasks. Some of this data may be wrong. Okay. So what does machine learning have to do with this? Well, we're trying to deal with the consequences of this problematic data. Again, we're talking about data with which the model has been trained. And some of this data is problematic, which can do what? It can cause a lot of different problems, societal problems, big societal harm. If you see it as an AI model safety problem, or as a critical infrastructure safety problem. So for example, you can have unauthorized use of data, or use of private data being publicized to the world with which you're not comfortable. We've heard stories about, for example, AIs being employed in the American judicial system, and they carry biases, and they're used, for example, in cases where they were helping a judge to decide whether somebody deserves parole or not. If this data is biased, then the judge's decision will be biased. Okay. You can think of problems with the original data, such, for example, in medical applications where the data is misclassified, that can cause misdiagnosis with respect, say, to the prediction of cancer, or mistreatments, or schedule in a hospital. If you think about critical AI infrastructures, a hospital, somebody can misdiagnose something, and then another AI will take this misdiagnosis and will schedule some particular treatment, which will be wrong and damaging, harmful to the person that's doing this, or even schedule operations, surgeries that have to take place, which are unnecessary, and so on and so forth. Okay. Or you can think about energy grids or transportation systems, and AI systems being interconnected to one another, and then having one failure in one AI system cascading down the chain of the interconnected AI models. So you can think, for example, of a localized blackout in an energy grid being actually widespread. Okay? Same with telecommunication infrastructures. So these are the consequences, and they're quite stark. Okay? They can be quite grave, causing societal harm. So then what is machine learning about? It's trying to address this need. So I hope what I just said so far with these couple of sentences points to the need that it would be great if we had this tool that can actually correct the behavior, the erroneous behavior of the model that is caused by this problematic data that was used during training. Okay? So that's what machine learning is about. Okay? We're trying to remove the effect of this problematic data, or as it's called, make the model forget the problematic data, or unlearn the problematic data. Okay? These terms are used interchangeably. Okay, with me so far? Okay, pretty straightforward. So I wanted to put everything in a global picture so you can see where machine learning comes into play. So everything starts with data. Using this data, we'll use some kind of a learning algorithm. And then basically we build, say, a deep neural network. That's a so-called modern AI, to do whatever, okay? Then we use this model to do our inferences, our predictions, or whatever, our classifications, whatever. Okay? And then, of course, we all know that new data may be coming in. Okay? Community has dealt with this for decades. So there are these, now they're called continual learning, or lifelong learning, or few-shot learning. So there is this collection of algorithms that deals with adapting the previous model, this previous model here, with this data, and update the model so it can continue making correct predictions, correct inferences. Okay? So that's pretty much the state of the art until this unlearning thinking came into place. And there's been research on this, serious research, 6-7 years now, but now it's really becoming a burgeoning field because of its importance, as I've indicated a couple of slides ago. So what completes this picture, this is need now to start removing data, or removing the effect of data, of this problematic data that I talked about earlier. So what we need is, we need a bunch of unlearning algorithms, which are in contrast with the learning algorithms, or the continuous learning algorithms we've known before, we know and love. And what this, using this, the data that we want to forget, to unlearn, and these unlearning algorithms, and also perhaps using the original data set or the model that we want to change, and the new data and the new algorithm. The goal is to produce this updated neural network. Okay? This updated model that will have unlearned the things that we want to unlearn. Okay? So that's what the goal is. And one thing that I want to stress is this notion of model recycling. We could, of course, try to retrain from scratch, as I will show in a minute. In other words, take the original data set, remove the data that we want to remove, and just train the model that you would, with your learning algorithm, on the difference of the original data set minus the data set that you want to forget. And that would do the job. Okay? Except that this is very costly. For example, if we're talking about large language models that you all know and love, training a large language model can take weeks up to months, thousands of GPUs, energy equivalent to it's estimated that training one version of ChatGPT takes about what the average house, what in New York City, the collective household use for 1 year. Okay? You don't want to do that. Now, if your data, if you're not talking about a large language model, then things are a bit not so expensive, not so prohibitive, but they're still costly in terms of GPU time, in terms of resources, in terms of the time that you have to wait there while the model is being retrained. Okay, so this is what the notion of model recycling is. So we don't want to do everything from scratch. We just want to basically take the previous model that we have there and slightly tweak it, given the set of data that we want to forget, so to get the desired effect. With me? Cool. All right. So, and we want to do this, of course, spanning different data modalities, which is another problem. For some of these data modalities and tasks, the unlearning problem is well defined and it's slightly easier, or we've made more progress, I should say. So whatever we're dealing with an image data set, say if you have a task such as image classification, and some of your images are corrupted and you want to remove them, so that's one application. Or you may be dealing with tabular data, kinds of stuff that we have in hospitals, for example, okay? Or in a database, in a relational database system, for those of you that are knowledgeable in this, and tabular data analytics tasks. Or you may be dealing with text, large text corpora, and large language models being trained on them, okay? This is what you want to do, okay? So you can have a bunch of NLP tasks, and what you want to do is unlearn the problematic data without actually hurting, damaging the general model's performance. More about that in a minute. Okay, so let's give an example with some image data. This example, by the way, came from the first workshop with colleagues from Google Research and Google DeepMind and some other academics and my group at Warwick. We organized the first NeurIPS competition on Unlearning. So you have the link there. If you're interested in this, I urge you to go and take a look at it. There was about more than 1,200 groups participating in the competition. About 1,800 researchers from all over the world, okay? It shows how interesting this problem is to the community. Okay, so we start with some image data set there. This pointer is a problem. So we start with some image data set there, and we train the model. And then somebody says, okay, I want defines a forget set. The bunch of images here, it's the first image that you see there that you want to remove, okay? And then basically, given all of this, as I said earlier, you want to come up with an unlearning algorithm. And using this unlearning algorithm, basically, you want to come up with the so-called unlearned model. And as I mentioned earlier, the brute force solution to this would be basically to take the difference between the original data set and this forget set and retrain the model from the beginning, okay? And that basically uses your learning algorithm from A, and you would get your retrained model. So how do you know if you've done a good job? How do you know if you succeeded? Okay, so this is a big part of what we mean by unlearning. So we could say, for example, are these models the same? Any takers here? Do you think these models will be the same? No, they will not be the same. Well, even what does it mean? I mean, if I change, when I was doing this learning, using my learning algorithm, or this particular data, if I change the seed before I started training, or the mini-batch size, or the learning rate, or these hyperparameters, the values, then I would get a different retrained model there. So what does that even mean? So the question itself has no meaning, okay, which is part of the problems of defining what unlearning is. Okay, so the answer here is no. So these models cannot be the same. Well, then what? How do we know that I've done a good job, right? So,
excuse me, why do you say cannot be?
Because there is a randomness inherent in neural network training, okay? So it's really doesn't make sense to expect that this would ever be the same, okay? So instead of asking, look at these models, we don't ask if they're the same or how close they are, but what we can do is make this more mathematically tractable. Somehow generate distributions from the outputs of these models, and then we can start playing with notions such as how close are these distributions? That's something that mathematicians can help us with, okay? And it as a problem makes much more sense. There's many different ways to define, from statistics to define how close the distributions are, and so on and so forth. Okay. So coming back to our image data set example, so we have the retrained model there, which serves as the oracle, okay? And we have the unlearned model after we apply that unlearning algorithm, and we ask the question, and we basically say, this unlearning algorithm must be such that the retrained model and the unlearned model are as close together as possible. In other words, the distance is as small as possible. Okay? Or, another thing you can say is, listen, in the end, what I care about is the accuracy of these models. Okay? The performance of these models. And now, I don't care about how the models look internally. Okay? If the models can actually predict the right thing at the right time with the right input, then that's all I care about. So basically, what then we're saying, this unlearning algorithm must be such that it guarantees the same accuracy. And what does accuracy mean here? We have actually three different things that we have to worry about. One is on the retained set, that is, on the data that actually remained there after we want to remove the data that we want to remove, the problematic data, we want the accuracy to be as good as, as high as the accuracy in the retrain. So we don't want to damage the accuracy on the retained set because we removed some examples that were problematic. Also, we want the accuracy on the forget set to be the same, and we also do not want to hurt generalizability. So if we take an unseen examples from an unseen data set and we give it to an unlearned model, we would like to see performance accuracy that's as close to the accuracy that we would see if we had just basically retrained the model. Okay? So that's another way of viewing how we can actually characterize the performance of unlearning and have some confidence with whether what we've done is actually correct. A point here worth making is that we actually, this is very difficult to achieve, but because for time, let me move on and I'll get back to this in a minute towards the end. Okay, so I didn't want to just stay at this high level, so I just wanted to give you a glimpse as to what our solutions are, what some of the state-of-the-art solutions are, and what do they look like when you're dealing with different problems, with different learning tasks, with different modalities. So if we look at the image classification problem, okay, so I have a bunch of classes, I've trained on a bunch of images, and I want to basically give it a new image, I want to say which class this image belongs to. Okay? So this is basically is the essence of a paper that we presented during last NeurIPS. It's no longer the state of the art, but I'm just giving you, it was the state of the art a few months ago, but there is a lot of new papers coming in, no longer the state of the art. But I just want to give you a glimpse as to what the solution looks like. So assuming that I have this definition of that basically tells me how close two distributions are, okay? So this is a well-known, the Kullback-Leibniz distribution, okay? So it basically says that here, WO are the weights of the model, is my original model, and WU are the weights of the unlearned model. So given some input X, I want the probability distribution that comes from the output of the original model to be very close to the outputs of the unlearned model. That's what this thing says, okay? And this is what the solution looks like. This is basically what the paper proposed. Quickly, so there is three terms here. This is the loss function that you're trying to minimize when you train the neural network, and basically says that try to minimize the distance between the original model and the unlearned model for the retained data. And this is how you do it, by playing with this distance d that we defined earlier. For the actual retained data, try to also train the model that does well on the actual examples coming from the retained data set. And with respect to the data that comes from the forget set, these DF examples, then you want to actually maximize the difference. Okay? So basically you minimize the negative. That's why I've highlighted the minus point sign there. Okay? So this is like doing gradient ascent instead of gradient descent, for those of you that are in the know. All right? And if you want to see what the new state of the art is, it's more complicated, that's why I didn't present it here. I'll be presenting this in a couple of weeks in the next NeurIPS, okay, in Vancouver. So if you're there, come talk to me. All right, and to give you an idea of what a solution would look like in large language models, and when we care about, for example, forgetting memorized data for copyright reasons, and also for privacy, because if you have, there's a lot of research that shows that if the model verbatim regurgitates data about you, then there is a well-known algorithm that can basically identify who you are in cases where you will not want to do that. So the question is, I have a large language model that's been trained on this huge computer, say all of the web, all of the internet, and now I want to remove from it information that refers to me, or information that, say, comes from a source for which the model did not have access or authorization to use the data it trained on. You've heard, for example, the legal battles between the New York Times or various institutions and all these large language models like ChatGPT and so on and so forth. Okay? So the problem here is memorization. It turns out that the more memorized the textual sequence is, the more likely the model is to regurgitate this verbatim. So if I was trained on something that said, Peter was in London at the FTC conference on November 15th, and I want that to be known, okay? So if the model has seen this text sentence many times, then it's memorized it. And because it's memorized it, it will regurgitate it. So this basically is a formula. It may look a bit scary, but it's actually very simple. It says given given a sequence, a sentence of T words, T tokens, how likely it is, given the previous tokens, a prefix of the sentence identify the next one. So that's how you measure how memorized this particular sentence is. And the state-of-the-art solution, before we actually intervened, is basically said, you take a test segment that the model has not seen, and you take sentences from there, and you look what the model's memorization of this is. And as long as, for your forget set, you can achieve an average memorization level that is actually what you would see, it's less than what you would see from a test set, then that's fine, and the model, we can attest that the model has forgotten this. Okay? So the solution we presented a few months ago at the ICML conference, which is also one of the major machine learning conferences, is basically doing something like this. It basically says, construct this set, D gamma, where gamma is the highest memorization score you can actually deal with. And you can get this value from looking at the memorization scores from test data sets that the model has not been trained with. And then basically only for this gamma, do something like gradient ascent, which I alluded to earlier. This is not the complete solution, and then keep doing that until basically you get your forget set, the average, there will be no element in the forget set that has the highest memorization score. Okay? This is actually a very niche idea that deals with the fact that the previous state of the art, the notion of correctness was an average thing, and this average thing does not guarantee anything. So we came up with membership inference attacks that show that this breaks easily, and how to fix it, and this is basically how we fixed it using this per example notion of memorization. And if you want details, look at our ICML paper. Okay, so where are we? How am I doing with time? I'm okay? Yeah. Okay. So this is basically where we are. And there's many problems to be solved. There's many things we don't understand. We're not even sure that we understand what we don't understand at this point. Okay, it's a burgeoning, it's a nascent field, basically. But some of the things that are close to my heart and that are open problems are the following. First of all, how do we identify the problematic data? Currently, there are human-in-the-loop mechanisms where, for example, domain experts like doctors sit down and look what went wrong or what could possibly go wrong, and they identify problematic instances of the training examples. Okay? You can think of what's called red teaming efforts within organizations, where they create simulations for cyber attacks, seeing what the output of the model would be, or they basically feed the model, they create particular data instances, data inputs, where they feed it into the model and see how the model would behave. Okay? Or after the fact, when something has gone wrong, some medic sits there and says, okay, so this particular image was not good. Some of these have been automated already, for example, in electronic trading scenarios. you know which of the last few trades were containing outliers that led the model astray during its inference. But some of them are not, so it'd be great if we could somehow move this automation further much more, and perhaps some of the things that John will speak after me can lead to there. So the other thing is, we're talking about these modern AI models, but there's many different. There's a big variety of them, okay? So there is discriminative models, and you have different versions of them. Even with convolutional neural networks, you have different versions of different architectures doing these. And then you have, the generative models, which could be, diffusion models or transformers, whatever. Again, this poses different problems, okay? So defining the problem for generative models is usually differently defined than the model for discriminative models. For discriminative models, you have access to the original data, typically, okay? And the original training data, and you can say, oh, these examples were bad, so please take this out, unlearn these. For generative models, you don't know what data the LLM has been trained on. So actually, the problem there needs to be defined as if something is generated, I didn't like that was generated. So you can ask the model, don't generate anything like this. But what does that mean, right? So the problem is that internally, the model has some weights, and these weights are important not just for one example, and that's for some examples. They're important for many different examples. Some of which you may want to unlearn, but some of which you may want to still know about how to deal with them. Okay. And also, so you can see it as an alignment problem. For example, make sure that what the output of the model is, an LLM, aligns with human values. So you don't want to generate toxic language or images with extreme nudity if you're using an educational tool for primary school students, for example, right? So things like this, or you want to avoid copyright, and so on and so forth. And the definition there changes. So we lack crisp definitions for what is the difference, at least, of the unlearning definition in generative models versus the definition that we're more comfortable with for discriminative models. So we have some work there. I really do not have time to discuss this. But this is also, this is currently an open problem. The other thing is about evaluation. So how do I evaluate if a generative model has actually, if I indeed have unlearned something? So the way this is done, so you have a generative model, you typically prompt it, you use some prompts, and you look at the output. So, and we all know the problem with this, right? So I don't know so there is very well-publicized examples where you know that the model, people claim that the model would, has been taught, not to do this, not to exhibit certain behaviors. And then when you give it some fairly naive initial prompts, the model indeed behaves well. But then when you engage with the model, you can actually, if you spend a lot of time doing some clever prompting there, then you can actually get the model to do whatever pretty much you want. Okay? So there is this famous example where the model was trained now to produce obscene language. And after the first 3 or 4 attempts, the model was behaving nicely. But after n attempts, where n was about 20, I think, you could see the output of the model was really obscene. Okay? So it's prompting. So I guess this is a general problem with experimental science, with empirical science, right? So you only know it works for the tested data. So you have to be really imaginative and as exhaustive as possible with respect to what the test data is, which is a problem. The other thing is about coming up with a efficient algorithm to check for correctness. So I mentioned in the beginning that, even for discriminative models, we have this notion of an oracle. So if you retrain from scratch, then you would be fine, as long as you're close to the behavior of the retrained from scratch model. Okay? But then we said, you're better off generating a distribution and check for the distributions. What does that mean? It means that I don't have just one retrained model, I have thousands, so I can get the distribution for every input, and then I look and compare distributions. But then that means you have to train thousands of models to be able to check for correctness, right? And this may take until the cows come home. So again, coming up with enough performance metrics with appropriate performance metrics that will allow this to be done efficiently is a great ask, and it's a tall ask for now for the community. And going beyond unlearning specific examples, such as, for example, unlearning entities, you may want to ask the model to forget, okay, don't say anything about Peter, okay? I don't want people to know that I'm a professor at the University of Warwick. And now we can do this, okay? There are algorithms that does this. So when they talk about Peter, they will not say that he's a professor at the University of Warwick, okay? But they may say that Peter is a criminal, that's been convicted of killing 10 people, okay? Which is, we got it to not say what we wanted it to not say, but it can hallucinate and say things that, I can assure you I have not killed, many people, okay? So, and also you want to forget associations, that Peter visited so-and-so in London on November 15, 2024, okay? That's much harder, okay? So I think I'm running out of time. I hope I at least got you to start thinking about this area, see about what some of the solutions may look like, and have a think about the many outstanding problems that are out there. Thank you for your time.
Thank you. Thank you, Peter. Wow. Well, about unlearning, we learned a lot there. Thank you. Yeah. Do we have any questions for Peter? Over there. Yeah. We don't have one, so I'm running over. Here you go.
Hey, great talk. Thanks a lot.
Thank you.
If I'm understanding correctly, some of the techniques that you're talking about are subtractive in nature. So you're trying to remove information that has been encoded into the weights of the model. As I'm hearing you talk about this, I'm curious, are there any additive techniques that you've explored such that maybe the model is missing information that might cause it to output harmful output, for instance? And are there any techniques to introduce that data into the model additively without having to retrain all of ChatGPT, for instance?
So that's a really great question. The short answer is, to my knowledge, no. But the point that you bring up is sometimes you can forget by adding the right information is a very important one. And I actually cannot thought about that, so that's a great idea. So thank you for that. So what I do know is there are techniques that basically do something what you say with the additive, but in an adversarial way. For example, I manage now to have my model forget something. The original model can associate that something with something else. So I can introduce new information to it, and then transitively the model can pick up again and undo the unlearn. So it's again with additive information, but in the other direction for what you were pointing. But this notion of actually adding information that will help me unlearn, coupled with other information there, I think it would make a great PhD topic. Thank you.
We got time, for one more quick question. Here you go.
Thank you very much.
Thank you.
This is a very brilliant presentation. And I must say you are trying to solve a very difficult problem. I just want to ask, do you have case studies where you have actually applied this process, the whole life cycle of the unlearning, that maybe we can study so that we can gain a better understanding? It would be good if you can refer us to such papers. Then the second thing I want to ask is, how do you actually identify the problem? For example, some bias in data set are inherent. How do you identify such bias and also quantify them? Thank you.
Yes.
Good questions. How do we know there's bias? Yeah.
Okay, so starting from the second one, this is actually the first item that I actually pointed out that we need additional research on to automate these identification problems. I can tell you how people do this now, depending on different applications. They use, as I said, red teaming. So basically, a bunch of experts get together, and they either create with simulations to see what the output of the model would be, or basically they come up with interesting corner cases for examples, and they try to test how the model would behave. And then they say, oh, okay, so for these types, then we identify there is a problem there. So that's, I know, a bit hand-waving. Medics do a better job. So for example, there are medics there that actually say, oh, I know this image. They look at the model misfiring. okay, the inference being wrong, and they say, okay, so I'll go back and say what caused it, and then they looked at images, and which is a painful process, and they can identify the images that were wrong, or some of the images that caused the problem. But in general, this is not possible. It's very human resource constrained, and we need more work on this. That's why I identified as a key problem. Now, with respect to the first issue you brought, if I understand correctly, I mentioned already a couple of our papers that we have in the last 2-3 big machine learning conferences. So you can start from there. You can see exactly what we've done and what the related references are there. Okay? Thank you.